My name is Zhiyun. This work is done by a group of researchers at UC Riverside. So we all love our smartphones. We use them every day, and we can't live without them. And I love my Android phones, especially because of its flexibility and openness. And it's great to see that Android has dominated the market over the past few years. But not so much about its security. So why is security so challenging in Android? Well, one of the reasons is that it's extremely fragmented and customized. As we can see in the figure, it shows the popularity of different Android phone models based on the market share, and it's obvious how serious the problem is. And another problem is that the Android OS update process has been slow, which leaves the vulnerabilities exposed for an extended period of time. Now, this problem has been improving significantly since the monthly security update program introduced by Google, but its mileage varies depending on the vendors, and it's extremely costly to keep up with the large number of phones that every vendor produces. So due to the open nature of Android, everybody freely puts whatever code they want into their customized Android code base. Specifically, cell phone vendors such as Samsung, LG, chipset manufacturers such as Qualcomm, and even mobile carriers such as AT&T and T-Mobile will all customize Android code base. So this is great for business and users because we have a lot of choices, but not so much good for security. So as it's really hard to make sure that everybody is on the same page and vulnerability free. So we now turn to kernel or driver vulnerabilities because we're interested in root exploits. To understand how the kernel might be target of attacks, we checked very quickly on the Android security bulletin in the past 3 months and add up how many CVEs there are that can lead to elevation of privilege and therefore potentially root exploits. And surprisingly, we found more than 100 of them in the last 3 months. And most of them are in the drivers and in the AOSP Android. So this is excluding Samsung or Huawei specific vulnerabilities. It also doesn't include the closed source components of the drivers. So you can imagine with customization how bad things would be. Now, because there are so many vulnerabilities in the kernel and drivers, there have been many root exploits developed over the years that can successfully root a variety of devices. And they're actually heavily abused by malware. As we know, once the malware obtains root privilege on a device, they can basically do whatever they want. They can be persistent even after app installation. They can do keylogging, ad injection, you name it. With some advanced techniques such as obfuscation, anti-debugging, or anti-virtualization, it's actually very difficult to detect root exploits or malware that contain root exploits. Furthermore, some exploits may be downloaded dynamically after checking if it has a suitable exploit for the underlying device. And if not, it simply doesn't trigger any real payload. So all of these factors together makes it really challenging to detect root exploits. And oftentimes, malware with root exploits can stay alive on the market for months before being discovered and taken down. For instance, last year there's this famous malware disguised as Pokemon Go guide app, which has received more than 500,000 downloads before it's taken down. Unfortunately, this is not the first time, and it won't be the last. Now, our goal is to basically develop a cloud-based app screening system similar to that of Google Bouncer, which addresses all of the challenges mentioned above. And we don't want to be overly ambitious. Here we just want to detect exploits against known vulnerabilities. So 0 days are out of scope. Fortunately, most Android malware actually mostly exploit known vulnerabilities based on what we know so far. and it's economically favorable that way. So let's talk a little bit more about Android root exploits and its unique challenges. Interestingly, due to the fragmentation and customization of Android, it's challenging to both write and detect root exploits. Now, from the attacker's point of view, it's great to be able to write powerful exploits, but since there's so many different Android devices on the market and so many different versions, you don't really know which devices are vulnerable to what exploits. So for instance, there can be a device driver which is vulnerable device driver, which is only present on specific types of devices. Now, the second problem is, even if we know that the vulnerability exists on a device, root exploits often need to be customized or adapted for that specific device. In fact, according to our previous study, we show that there's this one exploit which has extensive adaptation, as shown in the figure. So this figure shows across different Android kernel versions how many different exploit variants are developed. And the main reason for these different variants is that kernel memory layout can be different in different versions and different configurations. So how do we detect such a variety of root exploits in Android? Well, a naive solution is to buy and build a farm of Android devices with varying models and versions, and just screen apps on every single device, and hopefully one of the devices would be able to catch a real exploit. Well, obviously that's not really cost efficient, and it's probably a huge waste of resources, especially given that the number of Android devices continues to expand. Or alternatively, we could actually build a single analysis environment that can prepare itself to look like any of the individual Android phones. So that way, we can morph the environment according to the specific requirements of any exploit and hopefully be able to trigger them. So how do we build such an analysis environment? Well, fundamentally, we have to be able to emulate the correct underlying environment and program preconditions to guide the execution of root exploits to reveal its malicious payload. And generally, we have to first prepare the device environment to make it look like a target device type and model. And often in the malware, as we mentioned, there's a check of the underlying environment to determine whether and which exploits to launch. And secondly, we need to make sure that the program conditions are satisfied in the root exploit itself. As an example, if an exploit depends on a vulnerable device driver, then when it's trying to open this device file, even though our physical analysis environment or physical device may not have this exact vulnerable driver, we would still have to fake the existence of such a device. Otherwise, the exploit just aborts. So essentially, this is an input generation problem in the sense that we want to provide the malware expected input of the device environment and the program preconditions to guide its execution. Now, in this case, we note that the input is actually system call returns because we control the analysis environment by exposing different things through the system call interface. And that determines what the malware and the root exploit would do. But the key question here is, where can we collect such information? How do we know what environment and preconditions to prepare for different exploits, as there's so many of them? Well, our key observation is that in the Android world, due to this challenge of writing exploits for many different devices and the fact that users have legitimate needs of rooting their own phones, some large companies actually have started to develop and package root exploits in the so-called one-click root apps. I'm not sure if you've used it. Basically, you download this app, click a button, your device is rooted. It's pretty neat. I use it myself. So some app actually claims that they can support or root more than 100,000 different Android device models. That's pretty impressive. And in our prior work, we have analyzed a single one-click root app, and we managed to extract 167 exploit binaries, which belong to 59 different exploit families. And in case you're curious, users download such apps to root their phones for various reasons, such as removing bloatware or unlocking new features. And these apps are completely free, and everybody can download them. And these large companies basically have this business model to promote additional apps after your phone is rooted. For our purpose, though, these root provider apps are ideal places to obtain the data about the environment and preconditions of different exploits. Our second observation is that many root exploits are reused. This is because developing root exploits and adapting them to different phone models is an extremely challenging and resource-intensive task, as we just mentioned earlier. And there's a strong incentive for malware authors to copy root exploits from either the public internet or from these one-click root apps. So the conclusion, why not we just learn from these one-click root apps to understand the root exploit requirements? And given that their exploits are so diverse and most likely copied by malware. So we did exactly that. And we built a system called RootExplorer that takes advantage of the power from such professional root providers. Now, first of all, we have this offline learning phase versus this online testing phase. During the offline phase, we take a one-click root app, extracts as many root exploits binaries as possible. We process them as necessary to deobfuscate the binary. And then for each of the exploit binary, we extract the devices and the description of the exploit in the form of behavior graphs, which I'll talk in a bit. It not only captures the signature of the exploit, but also encodes the program preconditions that we just mentioned. And then in the online phase, our analysis environment takes all of the information learned in the offline phase and get ready for screening Android apps. So what is this behavior graph? Well, traditionally it has been used for capturing the malware behaviors. For example, clustering different malwares according to their behavior graphs. And this is done by monitoring its system calls. And this behavior graph is suitable for our purposes as well, because root exploits have to interact with the OS through system calls, right, in order to compromise it. And this representation encodes both data and control dependencies and are robust to simple reordering of system calls that may happen in malware. So in the figure, we show that this is a real behavior graph or partial behavior graph of a malware, a root exploit. As we can see, two different files are opened, their names shown on the left. And the first proc file is opened and read to extract an address, which is then used later on. And the second file, which is a vulnerable device driver, which is checked for existence first, and then opened, and then mapped by taking the address earlier, and finally be able to do some magic and then gain root access. So this is a pretty simplified example. So note that since the exploit binaries are already deobfuscated by us, right? So we can actually statically analyze these binaries and extract such a behavior graph. Right? This is not normally possible because in malware analysis, most likely we do not assume that malware is already deobfuscated. But in this case, because we extract binaries from a single app and we know exactly how their binaries are obfuscated. So it's good that we now have a way to capture the root exploit behavior. but it's not enough for our analysis environment to guide the execution of root exploits. As mentioned earlier, what we need is to prepare return values from system calls, right, as input to drive their execution. So how do we know what to return? Well, we have to do symbolic execution. So let us look at a concrete example. We see in this case that a proc file is read, and some data is being used to determine what to do, right? In order for the exploit to continue executing, for example, this variable line has to contain some specific content. And our goal here is to find out what string to return when readLine is called. So let us walk through this example. Our first goal is to identify a feasible path, preferably shortest path, that can lead to the success of exploit. And typically in these binaries, it's well defined where the success point is, so we can do that. And assuming we have a path already, we'll just walk through the path and collect what we know about the return value line. For example, when readLine is first called, we want the while loop to go to the true branch, and therefore we have to make sure that line here cannot be null, right? But we don't know much more about it at this point. And then we keep going. We see that there's actually a substring search inside line. And in this case, because we also want to go to the true branch of the if statement, we have to make sure that the return value of this string search also has to be not null. And basically, we also know, and further, we know that the line has to contain this specific substring kernel code, right? And if we keep going, we can see that it makes an invocation of getAddress, which goes inside and makes this A2I call. So what does this tell us more about the line? Well, it says that the buff has to have at least 20 preceding characters. And basically, that means line also has to have 20 preceding characters before the kernel code. Well, then, what is the end result? Well, the end result would be something like this. We have 20 unconstrained characters followed by kernel code. And here, the reason this first 20 characters are unconstrained is that A2I would basically return a legitimate number no matter what. Of course, if the address later is used in anywhere besides system call parameters, then we would have to further constrain these first two characters. OK, so our implementation, basically for the offline learning, we have developed a custom symbolic execution engine based on IDA Pro. We're exploring the possibility to port it to Anger, but didn't have enough time yet. And for online learning, we basically built a kernel module that does system call hooking, which is fairly standard. And we built a background service that runs in user space, which communicates with the kernel module and decide what to do for every system call invocation. And it's also responsible for monitoring and matching the behavior graph. Basically, when we see that the entire behavior graph has been matched, we raise a flag and say this is a root exploit. Experiment setup. Although our system actually runs on both real phones and Android emulators, in this case, we use Android emulators because we want to run more experiments in parallel. So to make the environment more realistic and robust to emulator fingerprinting, we load the emulator with files from real devices, such as call logs and messages. We even give real IMEI number to the emulator and then load appropriate build.prop file, which is commonly used to detect the type of Android devices and models and versions and so on. Since we're doing dynamic analysis to detect Android root exploits, we need a way to drive the execution of the app, since the root exploits may not be exposed right after you open the app. So to do that, we use droid-bot, which can randomly interact with the UI and then generate system events according to what the app listens to and reacts to. So we run every app for 10 minutes and check if it contains root exploits. So our evaluation data set, we have a training set of 167 exploit binaries, as we mentioned earlier, from that actually belong to 59 families. These are all extracted from a single one-click root app. And for testing, we actually have both positive samples and negative samples, as well as the gray samples. So for positive samples, we take proof of concept root exploits from the internet, the GODLESS malware, and 7 other one-click root apps. For gray samples, we take about 1,500 malware samples from an antivirus company that they suspect the malware might contain root exploits. And we took 2,000 recently uploaded apps from an unofficial Android market as well. For negative samples, we basically go to Google Play and download the top 1,000 free apps and hope that they would not contain root exploits. Otherwise, I think we're in serious trouble. So how do we evaluate these positive samples? Well, first of all, we downloaded and compiled several root exploits from publicly available source code, and then check how well antivirus software can detect them versus how our system can detect them. So as we can see for the table on the left, it shows that when we compile the source code with debugging options on, VirusTotal can basically catch all of the exploits. But when we compile the exploits using obfuscated compilation option, then VirusTotal actually cannot detect 2 of them already, half of them. But if you use our system, RootExplorer, we're able to detect 100% no matter how you compile the code. And then for GODLESS malware, this is actually a famous malware that embeds a whole bunch of root exploits that can target different target devices. And we observed that for 5 different emulated devices, we can actually trigger very different kinds of root exploits. And we also put it to test. We also put 7 other one-click root apps to test. And we can see the same thing here. Different one-click root apps would be launching different exploits against our device. So what about the gray samples? Well, remember we had around 1,500 malware samples and 2,000 apps from third-party Android market, and we basically test them on an emulated Samsung S3 device to see if any of the apps actually try to root the device. It's actually very difficult to find a Samsung S3 device now, so I think using our system is actually pretty nice. Right? You can fake whatever device you want. So we actually are able to detect 2 different apps that are flagged to contain root exploits. One is this Wi-Fi analyzer app from this mobile market, which actually has this ping-pong root exploit, which is very powerful. And we also detect this flashlight app from this malware sample that targets a specific device driver that's present only on the Samsung S3 device. And interestingly, it turns out that this particular exploit is not triggered right when the app is opened, and in fact, it's triggered only when it receives the boot complete event, which means that when the phone is just booted. And we confirm these results with VirusTotal and an antivirus company that these are indeed malware containing root exploits. So in conclusion, due to the unique landscape in the distribution of Android root exploits, we designed and implemented a system, RootExplorer, that can learn from these commercial root exploits and detect similar root exploits in malware. And we showed that this is an effective solution as we were able to detect real-life malware on the third-party market. We believe the system has the potential to be used in practice. And with that, I want to thank you for your attention, and I'll be happy to take questions.
August Regis Google. So early on in the talk, you gave the example of the Pokemon Go encyclopedia thingamajig app that had a root exploit for like 9 months. Did you try RootExplorer against it, and did it detect it?
You mean, did we try to upload an app on Google Play and see?
No. Did you try to run RootExplorer against that app?
Sorry. We were unable to locate a real binary, unfortunately.
I see. Thanks.
I have a question for you. I guess you have this unique insight into the different one-click root apps, and you gave us some hints that there's some of the exploits there, some of the vulnerabilities they're exploiting are overlapping among these different one-click rooting apps. Others are distinct. How different did you find the basically vulnerabilities these apps were exploiting?
Well, we haven't analyzed many one-click root apps because it's quite laborious to do that. So, but based on the fact that by learning from one root exploit, by learning from one-click root app, and we're able to detect similar exploits on other one-click root apps, it already tells that they're quite similar.
Okay. All right, and with that, let's thank Zhiyun.